Hello. So I'm still isolating, so I'm having to do the introduction to quantum physics from afar. So yeah, this is today. Quantum physics, energy of a photon, and the photoelectric effect. Hopefully, you remember all the stuff about waves, because if you don't remember the stuff about waves, all this is going to be a bit tricky. So quantum physics, the energy of a photon, and the photoelectric effect. Let's let's just perhaps get a few definitions first. Excuse me, this is first of all, quantum. What does quantum mean? Basically, it just means an amount, a small amount, just generally quantity or amount. In physics, it is the smallest quantity of radiant energy equal to Planck's constant times the fundamental frequency of the associated radiation. Basically, it just means quantum physics means the physics of the very, 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 very small, but defined smallness. And we're going to start off with a few quotes about quantum physics and quantum mechanics and the quantum world, because there we go. For those who are not shocked when they first come across quantum theory, cannot possibly have understood it. Niels Bohr basically say, when you first hear quantum physics and you don't go, then you've not got it right. And the classic Richard Feynman, I think I can safely say that nobody understands quantum mechanics. Having studied quantum mechanics or attempted to study it at university, I can safely say I didn't have a clue what was going on. It's supposed to be difficult, and it's supposed to not necessarily make sense. In the sense of fits with the normal way of the world. So, yeah, expect maybe the unexpected. Here we have some of the famous faces related to the quantum world. Paul Dirac. Sorry, things making strange noises. The aim of science is to make things difficult. To make difficult things understandable in a simpler way. Actually, he was talking about poetry, but it's a good, interesting segue. Trying to explain a very complicated thing in a simpler way. You can judge by the end to see whether I have done this. Albert Einstein. One of his discoveries gave birth to the quantum thing, photoelectric effect. Problem with that is he hated the quantum effect, and it disagreed with his other things. Quantum and relativity do not agree with each other. They just don't fit together. There's a lot about probabilities and things like that. He says, "Will you believe in the probability of a theory which is able to give a complete description of reality, the laws of which establish relations between the things themselves and not merely between their probabilities? God does not play dice." He wasn't a fan. Niels Bohr, "Don't tell God what to do." Those who were not shocked by quantum physics could not have possibly understood it. Werner Heisenberg. We have to remember that what we observe is not nature itself, but nature exposed to our method of questioning. Basically, quantum physics is not necessarily about what's happening, it's about what happens when we look at it. Heisenberg's uncertainty principle is all about how things change when we observe them. Erwin Schrodinger, the Schrodinger's cat. Schrodinger's cat is a analogy used to describe quantum physics. A bit of a piss take. They're like, "Oh, how stupid is this?" And unfortunately, it has stuck. Kind of like the name The Big Bang. He does not like it. "I'm sorry I had anything ever to do with it. Had I known we were not going to get rid of this damned quantum jumping, I would have never involved myself in this business." If you study physics university, you will learn a lot about Schrodinger and his wave equation. Louis de Broglie, look at his forehead. Electrons should not simply be considered as particles, but that frequency must also be assigned to them. Won a Nobel Prize for realising that electrons aren't just particles. And Max Planck, who is obviously some sort of vampire. "Physics is dead, young man. It's a dead-end street. From an unknown teacher to Planck, considering physics at the turn of the 20th century." This is the famous, the Physics Savoy Conference, 1927. Probably the smartest people in the world. We have people like Schrodinger, Pauli, Heisenberg, Paul Dirac, Max Born, Louis de Broglie, Niels Bohr, Max Planck, Marie Curie, Lorentz, Albert Einstein, just to name but a few. The other guys, sorry, didn't get a look in. So it all Did it all start with this? Probably started this. In 1905, this is a young Albert Einstein. In 1905, Albert Einstein published 4 papers in the same year. He wasn't even working as a scientist, he was working in a patent office doing patent work. And he self-published these 4 papers. One of them was Brownian motion, one was relativity. What was the other one? Can't remember. And one was the photoelectric effect. He won the Nobel Prize, 1921, for the photoelectric effect. Basically, the photoelectric effect is that light energy is carried in discrete quantized packets. Basically, light is not just as a wave, but it is a packet, a photon, a bit of a wave. And so, with it comes a simple equation. If we want to work out the energy of a photon, you need to know a new constant, and this is H, Planck's constant, after Max Planck. It's a really, really, really small number, 6.63 times 10 to the minus 34. So to work out the energy of a photon, you do 6.63 times 10 to the minus 34 multiplied by the frequency of that photon. If you remember the frequency of something, actually I don't remember the frequency of any of those photons, but the wavelength of light, we can have anything between 400 to say 700 nanometers. So if you use V equals F lambda, so V over lambda equals F, that gives you, well, why don't you pause and work out the energy of a photon of 400 nanometers and the energy of a photon of 700 nanometers. In fact, you could rewrite this equation. So E equals HF, but if F equals that, we're going to have E equals hc over lambda, and c is the speed of light. The pen's quite thick, I might change that. So E equals hf or E equals hc over lambda. Go on, have a go. I'll do it. Let's get my calculator. So we've got this one is 4.97 times 10 to the minus 19, and two 84 times 10 to the minus 19 joules. Okay, so the first thing you should notice, if you got it correct, is that those are really ridiculously small numbers. When you're dealing with energies relating to photons, the numbers are very, very small. In fact, they're not useful at all. So there is a conversion that we do. We don't talk about things like 1 times 10 to the minus 19. Come on. We do something called the electron volt. The electron volt is the energy change of an electron when it moves through a potential difference of 1 volt. Since 1 volt is 1 joule per coulomb and the charge of an electron is 1.6 times 10 to the minus 19, we get 1 electron volt is 1 joule per coulomb times the charge of an electron. So basically, you take the value 0.84 times 10 to minus 19 and you divide it by the charge of an electron, and we get 1.78 eV, 1.78 electron volts. It makes it much easier to handle these kind of numbers. If you're doing a calculation with electron volts, with joules, and you get these really stupidly small numbers, spend a bit of time and do convert it to electron volts. It makes it much easier. Right before we go any further, let's do some more question practice. Oh, forgot to reset this. Okay, so here we go. Question number 1. Have a go. I'll give you a second. Find the frequency. Remember, you need Planck's constant. H equals 6.63 times 10 to the minus 34. So, please find the frequency of a wave with a photon's energy of 5.8 times 10 to the minus 19. Someone's at my door. Give me a second. Okay, so hopefully you've had a go at this one. Let's check your answers. Rearrange the equation. Frequency is energy over Planck's constant. Substitute in the values. And did you get the answer? 5.4 times 10 to the 14 hertz. If you did, well done. Okay, this one. What is the energy of a photon in a wave of a frequency 4.8 times 10 to the 14? Put your numbers in. Go on, have a go. I'll wait. Don't just wait for the answer. Do it. Ready? Equals HF. Don't need to rearrange. 6.63 times 10 to the 30 minus 34 times 4.8 times 10 to the 14 equals 3.2 times 10 to the minus 19. Ooh, next stage, you could even convert that to electron volts. That is 2. Should have been able to work that out without a calculator. Calculate the energy of red light of frequency 450 terahertz. Oh, you have to remember your prefix. What is tera? It's above giga. Maybe that doesn't help. So work out, convert that, times it by Planck's. Give me an answer. Times 10 to the 14. Oh no, it's 450 times 10 to the 12 actually, isn't it? Times Planck's constant gives us 2.98 times 10 to the minus 19. Should we do one more? Oh. Green light, 580 terahertz. Go on, do it. Do it. Okay, have you converted it correctly? 5.8 times 10 to the 14. Then stick it in the equation, times it by Planck's constant, 3.85 times 10 to the minus 19. We're going to stop there. That seems to be plenty. Okay, so let's move this out the way. Okay, so this is actually, do you know what? There's another animation. Let's show you the animation. And golden leaf electroscope. And I'll explain what the golden leaf electroscope is. So basically, we have a box. Now the box has glass either side, so it's kind of wood, or I think we've got one at school. It's solid, like opaque material, wood, metal, plastic, something like that, on all sides, apart from the front and the back. So not all sides. 4. The front and back are glass, or at least transparent, so you can see through. And then going through the middle is this like a metal pin. Most importantly, this metal pin is isolated. Are the labels coming up here? It is isolated from the box. So although this is metal and this outside could be metal, this metal here in the middle and this metal do not touch. This is like a rubber insulator. It is not touched. At the top there is a metal plate. It's often a disc about that big, the size of, I don't know, a golf ball diameter. And then we have a little bit of gold leaf. Gold leaf is, thing about gold is it can be hammered ridiculously thin, just a handful of atoms thin. And so it's made of gold, but obviously it's incredibly light. And it's attached to the side, and then our box is, so it's a box. And so we've got this. Then what you do, the way you work this, is you take a polythene, I can't remember which it is, polythene, or you take a plastic rod and you rub it so it's statically charged. Now, the most important thing is you use the rod, you make sure the rod becomes negatively charged. You make sure it has lots of electrons on it. Rather than having the electrons rubbed off and becomes positive, you rub it with rub it so it becomes negatively charged. Okay, you then put the rod on the metal plate, and as you can see from the animation, let's just go back a bit. You put the rod onto the metal plate, and because the metal is a conductor, some of the electrons flow onto the metal, and it becomes negatively charged. Because it's negatively charged, what happens is the metal and the gold, both negatively charged, move away from each other. That's why your hair stands on end if you put your hands on a Van de Graaff generator, because you become overly charged and all your hair is trying to repel itself, and that's what's happening there. So the gold leaf will stand on end, and you take the rod away, and because there's nowhere for the electrons to escape, the gold leaf just kind of stays up. If you wait long enough, it will go down, but like hours. Now, the strange thing happens. If you shine ultraviolet light onto the metal plate, what happens is the gold leaf goes down. Like that. Now, the only reason it would go down is if the charge is removed. So what must happen? Let's go back. You shine ultraviolet light on it, the gold leaf goes down. That's because the charge has been removed. The gold leaf won't go back down unless the charge is gone. So somehow the electrons have been released from there, but there's nowhere for them to go. They're not connected to anywhere. There's no like loop, there's no circuit for them to go to. The electrons must have been released. It's worth noting that this only works in specific conditions. For example, if you put glass on the top of the metal sheet, glass absorbs ultraviolet light, so the electrons are not released, therefore the gold doesn't go down. Same thing. The next one is if you do it further away. If you move the ultraviolet light source further away, it still happens, but slower. So it's not about how close it is. Closeness just increases or decreases the rate. The most important part of this whole process, though, is it only works with certain wavelengths of light. If you shine visible light onto the gold leaf plate, nothing happens. Nothing happens at all. The electrons do not escape, and the gold leaf does not go down. This only works with the right frequencies. I did say at the beginning, if you make sure you put it negatively charged, if you do it positively charged, it doesn't work at all. So let's just move that out of the way. So basically what's happening with this photoelectric effect. So what I'm going to do is, see this section here, I'm going to draw it here, but zoomed in. So this is my plate, and inside the plate we have lots of electrons. And then we've got our rainbow. Oh, I could use the rainbow pen. Red, orange, yellow, green, blue, indigo, violet. Oh, sick. Ultraviolet. Oh my god, it's done it in the right colours as well. Infrared. Oh, I should have done those first. So, if what's happening is light's coming in, tick, 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 tick. It's hitting one of the electrons, and the electrons are escaping. Okay, so the light comes in, it hits an electron, and electrons are escaping. But if, like I said, if I did it with ultraviolet, light comes in, electron escapes. But if I do it with just green, light comes in, and the electron does not escape. Why? How does that happen? That's illegal. Well, it happens if our assumptions about light have been a little bit off already. Let's clear this off. Okay, so if light were a wave, I'm going to go back to green actually. If light were a wave, it wouldn't matter the colour of the light, because what happens is a wave is a constant stream of just energy. Is how energy moves from one place to another, particularly like infrared radiation or just not infrared, electromagnetic spectrum. If light were a wave, this green light, this green visible light would hit that electron, and as it hits the electron absorbs the energy. Now we know electrons must absorb energy because sometimes they escape. So electrons have to be able to absorb the energy. We also know they absorb energy because we do spectrographs where we can look and we see like bits of the light are removed. So we know electrons can absorb energy, but they can't store it. They're not like a battery. They can take the energy and they can do stuff with it. So if the electrons are able to absorb energy, and we've got this green light coming in, what should happen is, admittedly, when the green light first hits it, the electron starts absorbing the energy, and when it gets to just the right amount of energy, the electron can escape, and we have photoelectric emission. But that doesn't work. If we do it with ultraviolet light, electrons coming in. If ultraviolet light was also a wave, the same thing should happen. It should hit it, but it should be released faster. But what happens with ultraviolet is it releases immediately. Now, the theory works like if it's a wave, if light were a wave, it shouldn't matter the colour of the light. Any wavelength of light should be able to release electrons. But if light isn't a wave, what is it? Instead of it being a constant wave like this that goes on forever, it's in fact a bit of a wave packet, a photon, a tiny amount like this, a small piece of wave. Now, if we consider it in terms of green, when green photon comes in, the electron absorbs the green photon, but the green photon isn't enough for the electron to escape. The electron is bound, it's stuck in one of its energy levels, and it's not able to jump high enough to escape from the attraction of the nucleus, so it can't escape. So therefore, it just releases the green, nothing happens. Electrons are not batteries, they can't store the energy. They can, if they get the energy and it's useful, they can escape. If it's not useful, they can't hold on to it. With the violet, or ultraviolet light, it hits it, it's still a small amount, but the small amount means that it's enough. If that energy is enough to allow the electron to escape, then it can escape. If the light is not a wave but a wave packet, that means the energy is arriving in small chunks. If one small chunk of energy, E equals hf, the wave of a photon, is enough to release an electron, then the electron just takes the energy from the wave and releases it. If it's not enough, it won't release it, and then the light is re-emitted. And that's how Einstein got his Nobel Prize. He did loads of other really amazing things, but this is what he got the Nobel Prize for. And this basically says light isn't a wave. If light were a wave, red light would release electrons, blue light would release electrons, infrared would release electrons, because all that happens is the light, infrared hits it, and the wave goes in, and it charges, it gives it enough energy, and when the energy is enough, the electron releases. But if light was a photon, a small piece of a wave, the light comes in, it absorbs the small photon's energy. If that energy is useful, then the electron can do something, escape. If it's not useful, then the electron just has to give up that energy. It just spits it back out the other side. And that is the photoelectric effect. Light comes in, electrons go out, as long as the energy is high enough. And that basically proves that the photoelectric effect and that light is not a wave, it's actually a wave packet. It's made up of lots and lots of different bits of waves, but not one continual one. Lots of little bits of wave. And don't do any more. There we go. Do you know, we'll do one definition. So basically, the photoelectric effect works for some light or electromagnetic radiation. For example, red light will not release electron from lithium, but blue light will. So each metal or each material has something called a threshold frequency. If your frequency of light is below the threshold frequency, no electrons can be released. If the frequency of light is above the threshold frequency, electrons can be released. And we normally write the like this: F0. Frequencies below which no electrons are released from the metal is called the threshold frequency. Yeah, it's 25 minutes. That's a lot. It's a lot for one. There we go. I'll leave that with you, and just we'll do some more tomorrow. Okay, bye.